What I would like to do today is to start the discussion on third order nonlinear effects, which are very briefly introduced in the last class. So remember, the general expression for polarization is epsilon 0 chi e plus 2 epsilon 0 d e square plus epsilon 0 chi 3 e cube. This is the linear term, this is the second order term, this is the third order term. This term is absent in media possessing a center of inversion symmetry. So those media, the first nonlinear term is the E cube term, and this is the third order nonlinear effect term. Nonlinear effects. So if you take, for example, any liquid, glass, then it does not possess the second order effect. All media possess the third order effects. So even the glass that is used in optical fibers, for example, will possess this effect. And as I was mentioning, this causes problems in communicating through light using optical fibers. So what I would like to do is to discuss some of the effects that this leads to. We will not go into too much details, but I will present you some effects like cell phase modulation and four-way mixing that are apparent from this term here. Some of the applications which I gave first, the phase conjugation is actually coming from this term. So there are many other terms. Optical bistability can be used from this term and so on. So there are topics which I have given you which are effects of this in an optical system. Okay. So let's start with considering. So the nonlinear polarization term that we are going to look at is epsilon 0 chi 3 e cube. Now I'm using a scalar notation here, but if I were to write in a complete vector form, I would have to write like this: pi nonlinear is equal to epsilon 0 chi 3 I j k l e j e k e l. This was 2 epsilon 0 dij k e j e k. Now that's a chi I j k l e j e k e l. So that's a 3 cross 3 cross 3 cross 3 matrix. Okay, it's a tensor. And so this, at least some elements of this matrix are non-zero for every medium. So you can have, for example, the chi matrix for isotropic media, for crystals, for whatever it is, for different media, the chi matrix has some elements which are 0, because if you have a completely isotropic medium, a medium which has complete symmetry in all directions, then that symmetry should be represented in this matrix. Whether I choose xyz in this orientation or xyz in this orientation or any other orientation, the chi matrix should be independent of my xyz orientation. If the material is completely homogeneous and isotropic and it has no symmetry problems, axes at all. So by using the symmetry arguments, actually one can calculate the chi ijkl matrix, and exactly like what we did for the second order nonlinear effects, we would have to use the chi ijkl matrix along with the orientation of the electric vectors to calculate what are the nonlinear polarizations generated, and so depending on the material and the orientations, there will be polarization generated in the medium. Now we will not look at the details of this, but we will use this equation, the scalar equation, assuming that the chi 3 that I am using here is an effective chi 3 coming from one of the elements or a combination of these, just like we did for the second order effects, and E is the corresponding electric field, and P nonlinear is the polarization that is generated. So that will simplify the analysis significantly, and we will get to understand what the primary effects are and what does it lead to. So the first thing, let us start by, again, just like we did for second harmonic, let's start with a medium and launch a wave at frequency omega. So this is the medium possessing chi 3. There is no chi 2, there is no d element here. So the nonlinear polarization is epsilon 0 chi 3 E cube. So E is electric field, which is half E0 exponential I kz minus omega t plus complex conjugate. In the other case, it was epsilon 0, 2 epsilon 0 d E square. Now it's simply epsilon 0 chi 3 E cube. So that's the only difference. So what are the terms that I will get in the nonlinear polarization? Epsilon 0 chi 3 by 8. So I will have, so it's a plus b whole cube. So I have E cube, E0 cube, exponential 3i kz minus omega t plus complex conjugate plus, what is the term I will get? 3
mod of this whole square.
E0 square into
E naught cos kz 2 twice. Kz minus
okay, a cube plus b cube plus 3a square b plus 3ab square. This is the term that will lead to third harmonic generation. What is the phase matching condition? What condition would I have to satisfy if I want this term to generate third harmonic?
K is equal to 3.
The propagation vector of 3 omega term must be equal to 3 times propagation vector of the omega term. So can you tell me what is this in terms of refractive indices? N at 3 omega
Is equal to n of
is equal to n of omega. Okay, so if I want to use this process for third harmonic generation, I can do so provided I have this condition satisfied. Now usually in media like glass and liquids, this is never satisfied because n of 3 omega is not equal to n of omega because of dispersion. So usually this term does not lead to the generation of third harmonic. There is polarization, there is nonlinear polarization, but it does not lead to the generation of the electromagnetic wave at that frequency because you are not phase matched. Please note, individual dipoles are oscillating at frequency 3 omega. They are all trying to radiate at frequency 3 omega. But the radiation coming from all this collection of dipoles is cancelling off each other. And so there is no electromagnetic field at frequency 3 omega. So this term usually does not lead to any generation because normally I will not be satisfying this condition. So there is no problem. That is the third harmonic term. What about this term? What is the frequency of this? It's omega. So this is the nonlinear polarization at omega now. So what is the total polarization at frequency omega? So the polarization at frequency omega is epsilon 0 chi E plus epsilon 0 chi 3 by 8 into 3 mod E naught square E naught exponential I kz minus omega t plus complex conjugate. Now 3 mod E naught square is real. So it has the same term in the complex conjugate term. So actually this second term is plus 3 by 8 epsilon 0 chi 3 mod E0 square into, so if I write 3 by 4 here, so what is the remaining term? half E0 exponential I kz minus omega t plus Laplace conjugate, which is E. E is half E naught exponential I kz minus omega t plus Laplace conjugate. 3 mod E naught square is real, so I can take it out. It's common between this term and the Laplace conjugate term, and the remaining factor with the half is nothing but E. Now first note that this is a nonlinear polarization at frequency omega and propagating at a velocity omega by k. So what wave will it try to generate? It will try to generate a wave at omega frequency, because that's a nonlinear polarization at frequency omega, and it has a velocity omega by k, which is exactly equal to the velocity of the electromagnetic field at omega. It is automatically phase matched. This effect will always contribute, because even if I don't do anything, the velocity of this nonlinear polarization term is exactly the same as the velocity of the electromagnetic field that it is trying to generate, and it's completely phase matched. So I can write this equation as epsilon 0 chi plus 3 by 4 epsilon 0 chi 3 mod E naught square into E. So in the presence of this term epsilon 0 chi 3 E square, E cube term, it looks as if the susceptibility had got modified. The susceptibility was chi for if I neglect the third order effect, otherwise it is this. And how is susceptibility related to refractive index? So this is the effective susceptibility in the presence of nonlinearity. So how is refractive index related to chi, epsilon, the susceptibility? N square is equal to 1 plus chi. Okay, 1 plus chi. So let me, if I call this chi effective, chi nonlinear. So no, so let me call it chi prime. So this is one, this medium now has a refractive index n square, which is 1 plus chi prime, which is 1 plus chi plus 3 by 4 epsilon 0 chi 3 mod E naught square. What is 1 plus chi? The refractive index of the medium if you neglect nonlinearity. It's okay. Sorry, yeah. So yeah. Okay. So this is the, so 1 plus chi, I call it n0 square. N0 is the refractive index of the medium for low intensities. If E naught is very small, this term is negligible and the refractive index is N naught. So N naught is the refractive index of the medium at low intensities, and as you increase the intensity, the refractive index becomes a function of the intensity, and this is given by this equation. Now usually this term chi 3 is very, very small, and so this term is much smaller than the refractive index of the medium, so I can make an expansion and write this as n is equal to n0 into 1 plus 3 by 4 n0 square chi 3 E naught mod square this per half, so which is approximately n0 plus 3 by 4 n0 3 by 8 n0 chi 3 mod E naught square. Because this term chi 3 is very small, chi 3 times mod E naught square is very, very small. I'll give you some numbers. So this is an expansion, and I can actually relate E naught to the intensity of the wave. Intensity of the wave is nothing but n naught by 2 c mu 0 mod E naught square. Here I am using n naught, I am not using the modified refractive index because this change is actually extremely small. So n is approximately equal to n naught plus 3 by 8 n 0 chi 3 into 2 c mu 0 by n naught into I, which is equal to n naught plus 3 by 4 c mu 0 chi 3 by n naught square and I write, usually this is written as n 0 plus, where n 2 is this term here. So n 2 is equal to 3 by 4 c mu 0 chi 3 by n 0 square. So this leads to what is termed as intensity dependent refractive index. The refractive index of the medium gets changed if you change the intensity, and that comes in because of the chi 3 term. Now let me give you some values for N2. For silica, the value of N2 is about 3 into, so N2 for silica, what will be the unit of N2?
Meter square by what? By joules.
By joule? Meter square for what? 3.2 into 10 to the minus 20 . See, extremely small. So let me calculate the change in refractive index that will take place. So what value of intensity should I choose? So let me assume certain power focused into a certain area. Okay. So let me take a power of 1 watt. And what area should I choose? 1 millimeter square. Good. So the intensity will be, what is intensity in watts per meter square? So n will be n minus n naught. The change in refractive index because of nonlinearity is n2 times I, which is 3.2 10 to the minus 20 into 10 to the power 6, which is that's a ridiculously small value of change. But let me assume that I have this change taking place over a certain length of medium, and that is where the optical fiber comes into picture. I can have light propagating over a long length in an optical fiber without getting diffraction, without undergoing diffraction. For example, if I put 1 watt of power into an optical fiber, what is the area I will take? For an optical fiber, the area is, instead of 1 millimeter square, typically 100 micrometer square, even less than that. So let me take an area of, so power is 1 watt, an area of 100 micrometer square. So this is 10 to the power 10 watts per meter square, meter 10 to the minus 10 meter square. Okay, so delta n is equal to n minus n naught is equal to 3.2 10 to the power minus 20 into 10 to the power 10. Intensity is 1 by 10 to the power minus 10. So that is 3.2 into 10 to the minus 10. Not much bigger, but it's of this order. Now, in an optical fiber, the light can propagate over long lengths. So let me take a typical length of 20 kilometers. Okay, so I take an optical fiber. So I launch 1 watt, and this length is 20 kilometers. Now let me neglect the attenuation of the fiber. Let me neglect the fact that the power is decreasing as it propagates. If I neglect that, so what will happen? Suppose I start with 1 milliwatt of power, look at the output light, and I go to 1 watt of power, what will happen here? I launch 1 milliwatt, I have a light wave coming out. Instead of 1 milliwatt, I make it 1 watt. What change will I see here?
More than 1,000 times.
The power is more. Anything else I see? Numerical aperture is, you see, numerical aperture does not depend in principle on the power that I launch. That's fixed on the fiber. So what is the power doing? It is changing the refractive index. So what will it do at the output? Something will change. It will increase the refractive index. So what will happen? No, that change in refractive index, please remember, is 10 to the minus 10. So that cannot change the spot size much because the refractive index is 1.45 plus 10 to the minus 10. Exactly. If you have 1 milliwatt of power, the light comes out with a certain phase change. If you make it 1 watt, the output phase will change. What is the change in phase that I will see? How does the phase depend at the output depend on power now? Delta n into length. No, that's not change in phase. Something is missing. Into, right? So let me assume a lambda 1 micrometer. So let me calculate this. So 3.2 10 to the minus 10 into 2 into 10 to the power 4 into 2 pi by 10 to the minus 6. So about 12 pi. Huge change. Remember, pi phase change, you can go from maximum interference to minimum interference, and 12 pi is a huge phase change, and that's happening because of this factor here. This factor is 10 to the power 10. L by lambda is 10 to the power 10 approximately. Because the wavelength is very short compared to the length of propagation, the cumulative effect of this phase, of this change in refractive index can be very significant. So the output light at the output, the phase of that light output can be changed by changing the input power. What is it? What is the light doing? The light is changing its own phase. It's called self-phase modulation. The light enters the medium, changes its refractive index, and hence gets affected by the change in refractive index. And the phase at the output will change as you change the input power. It's called self-phase modulation. SPM. And that's a very important effect in optical fibers, that you can change the phase of the output light by changing the power. Normally you change the phase by changing the temperature of the medium, or putting a strain on the medium, or changing the path length, changing the wavelength. Here I am not doing anything, I am just changing the power level, the output phase changes. So for example, if I were to use this in a part of an interferometer, I can go from constructive to destructive interference simply by changing the power of the light wave, and which means I can switch a light from one path to another path. If it is a part of an interferometer, if it is constructive interference, it comes out here. If it is destructive, it comes out here. So I can go from constructive to destructive simply by changing the power level. That's an example of all optical switching. I can switch the light beam from one port to the other port simply by changing the power level of the light. So I'm not doing any other switching, and that switching takes place extremely fast because the changes that we are talking of are extremely rapid. These are electronic transitions, electronic effects, and these are extremely fast effects. So there's no restriction here of the speed. So it's very extremely high speed. So this is a very important effect, and this, for example, this change in refractive index I could have also done in the following way. For example, what would I have normally done? I would have solved this equation, del square E of omega minus mu naught epsilon of omega del square E of omega by del t square is equal to mu naught del square p nonlinear at omega by del t square. Remember this equation we had derived right in the beginning, where the electromagnetic field at a frequency and the nonlinear polarization at that frequency satisfy this equation. So in my case, E omega is equal to half E naught e to the power I kz minus omega t plus complex conjugate, and p nonlinear at omega is equal to half 3 by 4 epsilon 0 chi 3 mod E naught square E naught exponential I this is from this equation which we had written just now. So the nonlinear polarization at frequency omega is in the second term here, and that's what I'm writing with a factor of half outside. So I use the same procedure as I did for studying second harmonic generation or parametric amplification. I substitute E omega on the left hand side, I substitute p nonlinear omega on the right hand side, neglect the second derivatives of E naught with respect to z, solve the equation. Then, so let me give you the equation that I will get if I do this procedure. So what I will get is, this will lead to this. So I leave this substitution and simplification to you. So I get d E naught by dz is equal to I omega by c into intensity into E naught. So you just substitute into this equation, use the definition of N2. So what is the solution of this equation? If I is independent of z, if I assume no attenuation, what is the solution of this equation? E naught 0 into right? Just I take the E naught on the left hand side and integrate omega c into I are constants. So I get this integral, and so the E omega I can write expression now. I substitute this into this equation. This is the way E naught behaves as a function of z. Please note here the amplitude is remaining constant, the phase is changing depending on the intensity. So I substitute this term into this equation and write the total electric field expression. E of omega is equal to half E naught of 0 exponential I. Now I have k plus omega by c into I into z minus omega t plus complex conjugate. This E naught has an additional term here, z dependent term. I add that with the kz term, and what do I get? A propagation constant which depends on intensity. So if you define this as the propagation constant in the presence of the chi3 term, you can see that this leads to, you see, k omega by c is k naught, the propagation constant in free space. So the actual the propagation constant in the presence of this nonlinearity is k plus omega by c into N2I. K is the propagation constant for low intensities, which is omega by c into N naught plus omega by c into N2 into I. So this is nothing but omega by c into N naught plus N2I. Exactly what I showed you just now, that effectively the refractive index of the medium changes in the presence of this nonlinearity. Okay, so that's a very interesting self-phase modulation effect, and this particular effect leads to a couple of topics which I gave you: self-focusing, it leads to spatial solitons, it leads to temporal solitons, it leads to many effects. We will not discuss all this in the class, but I'll leave it as a topic for some of you to take up and read on your own. And it is simply uses the fact that the refractive index of the medium now depends on the intensity. Okay, there's a problem on some frequency generation. There's 1 watt of power at 1 micrometer and 1 milliwatt of power at 1.5 micrometer incident. And the process that takes place is some frequency generation, and what is the maximum power that is achievable at the some frequency.